Okay, so this is the third video in Chemistry 1-2 Elements, Basic Atomic Structure, and the nomenclature. And so we were talking about strong nuclear forces and why they needed to be so strong is because the force of electricity between protons, the repulsive force at the distance that they're at within the nucleus is so strong that they literally will just sort of repel and release lots of energy as they're doing it if they were not constrained. So there must be a lot of forces that hold these together, and we literally call these forces the strong nuclear forces. That's their name, the strong nuclear forces. And this must be true because at the small distances between the positive charges in the nucleus, which are about 1/1000th of a meter, the repulsive forces are enormous. The forces holding the nuclear particles together are literally called the strong nuclear forces. So that's what we need to write down in that space there. Just recognize that this is a lot more significant than you might think. Okay, so as far as mass goes, protons and neutrons have about the same mass. And the difference is small enough that we can really ignore it. So we're just going to say 1.67 times 10 to the negative 27th kilograms. Because the actual mass of these particles is so small and involves large negative exponents, designation of the actual mass is extremely inconvenient. Nobody wants to write out 1.67 times 10 to the negative 27th after every atom. Okay? And so we don't. We arbitrarily give it a new name and a new unit. We call it an atomic mass unit and say that the atomic mass unit of a proton or a neutron is 1. So this would make it extremely inconvenient if we had to do that. But if we just write 1 for the mass of a proton or a neutron, that's great. The other subatomic particle is of course, electron. And these are in constant motion around the nucleus. When we first started learning about these, we thought that just like planets circle the sun, we thought that these electrons had a defined path around the nucleus. We know now that in its motion, the electron can be anywhere within a certain space around the nucleus. And instead of picturing it as an orbit, we picture it more as its possible positions, more of its cloud nature. Here's what I want you to draw. So you may have to find some space on the diagram. So just a quick illustration of this. So on one side of the diagram, we draw our standard picture of an electron orbiting a nucleus. On the other hand, we want to picture the nucleus as most likely being within this muddled out space around the nucleus. Just draw until we get a cloud here. So the electron can be anywhere in this, in the further away or the closer I get, the more we're going to have problems. So go ahead and just draw this. This is the comparison that we want to make. The old way of doing things is the old way of doing things. The making of a cloud diagram gives us a little bit of a better idea of how the electron can move. And even that's not a great idea compared to what actually is. What actually is very difficult to draw. So we will in the future picture electrons as being in motion around the nucleus in a very haphazard way. They can jump from one spot to another in order to be detected. So go ahead and go back to the discussion and we'll finish up. Okay, so that's the orbital, not the orbit. And then electrons, of course, we know are negatively charged. Because of this, they're attracted to the positive charges of the nucleus. However, because of the type of motion that they're in, they have energy enough because of this motion, and they remain outside the nucleus. Another thing that we know is that in normal atoms, there are the same number of electrons and protons, so the overall charge of the atom is 0, or we say that it's neutral in charge. In contrast to protons and neutrons, however, electrons don't have much mass, and we consider them to be negligible, so close to 0 that we just say 0. The actual mass is 9.1093856 times 10 to the negative 31st kilograms. And so when we talk about the mass of an atom, we only consider the neutrons and protons. And we might want to ask about what fraction of the mass of the proton is the mass of the electron. And the way that we can do this is by comparing the exponents. Okay, we know that a difference of 1 degree as far as exponents go represents a value of 10. So if I had 1 times 10 to the negative 29th and 1 times 10 to the negative 30th, the difference would be 10, right? So the thing that was 1 times 10 to the negative 29th kilograms would be 10 times heavier than the thing that's 1 times 10 to the negative 30th. So we have something that is 1.67 times 10 to the negative 27th kilograms, and we have something else that's 9 times 10 to the negative 31st. Well, that's almost 1 times 10 to the 30th. So we're comparing 10 to the 27th versus 10 to the negative 27th versus 10 to the negative 30th. And so if each step is a difference of 10 times, 10 times 10 times 10 is 1,000. So the mass of a proton is 1,000 times greater than the mass of a proton or an electron. So the about what fraction of the mass of the proton is the mass of the electron? It's about 1,000th, and we know this by the difference of 10 to the third. So there's 3 degrees there, and each degree is 10. So 10 times 10 times 10 is 1,000. And then we, as we've already said a bunch of times, we define the atomic number as the number of protons, and each element has a different number of protons. And again, the same number of electrons as protons if it's a normal atom. But we will see that the numbers of electrons change. So we say that the number of protons is what defines what that element is. That's the only thing that we can use. Now, the atomic number is the main number in each element's box on the periodic table, and each box also contains the name of that element in a 1 or 2 letter symbol, and we already know that this is called the atomic symbol, right? Just to kind of cement that in, that represents the element. So while most of these symbols have some relationship to the name, a few don't. For example, element 11, sodium, has the name as a symbol of Na. And these odd symbols usually stand for the Latin name of the element. And the Latin name of sodium is natrium. If it was gold, for example, Au stands for aurium rather than gold. And Ag for silver stands for argentum instead of silver. So while the number of neutrons is usually close to the number of protons in an element, in some elements, the number of neutrons is more than the number of protons, especially as the atomic number increases. And we're going to call the sum of the numbers of neutrons and protons something special. We're going to call that the mass number. Okay, the mass number is the total number of neutrons and protons, and protons, again, remember, is the atomic number. And what that allows us to do then is be able to do a little bit of math to figure out some things. If I have, and let me just put this in a place where I can write. So if I have the atomic number, and I have the mass number, and I have the number of protons and the number of neutrons. Realize that if I have atomic number 3, and let's say I have lithium, that's atomic number 3, that means I have 3 protons. And then I say that I also have 4 neutrons. So 3 wasn't what we were supposed to put in, was it? So then I have 4 neutrons. Recognize that if I have atomic number 3, I have 3 protons, and then if I have 3 protons and 4 neutrons, that means I have a mass number of 7. Okay. Well, what if I have 28 protons and 31 neutrons? That would mean that I have 28 as an atomic number, and then also that I have 59 as a mass number. And that was element nickel. If I have 10, and I have 100 and keep forgetting these going back and forth. 119 is a mass number, and 50 is the number of protons. Then to find the number of neutrons, I have to subtract the number of protons from the mass number, and that would give me 69. And the number of the atomic number would also be 50. Okay? If I have 85 and 48, if I have a mass number of 85 and a number of protons of 48, that means 85 minus 48 equals 37. That means I have 37 protons, and so its mass number is 37. And then finally, if I have bromine and an atomic number of 35 and a mass number of 80, okay, the number of protons is going to be 35, and the number of neutrons is going to be 80 minus 35, which is 45. So you need to be able to do these types of calculations for me. Okay? So we'll go back to the main presentation here. And you would want to fill that in on your sheet. And then lastly, we're going to talk about something called isotopes. And just to see if you remember anything about this at all, isotope has a number of blank that is different from the normal number for that element, and we'll find out here as we go through this what that is. So a student will be able to compare the number of protons and neutrons in an isotope of the same element, understanding that different atoms of the same element must have the same number of protons but differing numbers of neutrons explains the decimal number observed for atomic mass of each element on the periodic table, and we want to know why that happens. And then how, given an atomic number and a mass number of a particular isotope, you'll be able to determine the number of protons and neutrons in the isotope 100% of the time. And then you'll also be able to explain in general terms how the atomic mass of an element is obtained given an element's various isotopes. Okay, so I don't need you to actually be able to do it, I just need you to explain how it's done. And so running to the end of the video here, I guess I do need one extra little video here. So we'll shut this one off and go to the next one.